All right, in this video, we're going to talk about decay, and that is with alpha, beta, and gamma. And so I'm just going to put down my little starter. And so obviously we have the alpha, beta, and gamma symbols. Alpha kind of looks like that little fish, or maybe like an A with an other tail. Beta looks like a capital B with a lower tail, and gamma kind of looks like a Y. Now, some of the other things that are used for alpha, you could use 4/2 with that alpha symbol, or 4/2 He, because it's also the same as a helium nucleus. With beta, it's going to be 0/-1 with the B. Sometimes they don't have that negative there, or 0/-1 with an E, because the beta particle is basically an electron. Okay, so if it's just beta by itself, you'll see the B minus. If it is in the nuclear notation with the mass and the charge, you're going to see 0 mass, and you're going to see the charge right there with just the B. And again, it is basically an electron. With the gamma, it's going to be 0/0 with that kind of Y-looking shape. And so gamma is not a particle, but it is an energy. It has no mass and it has no charge. So obviously, I want you to refer back to your reference tables. If you're in New York State, we use the chemistry reference tables. And table O, I'll try to zoom in on that for a second. I don't know if it will focus. But with table O, you'll be able to see all of those units. You'll also see the positron, you'll also see the neutron and the proton. And so those obviously are going to become important. And a lot of times in New York State Regents exams, they ask you about a balanced equation for decay rates. And so one of the things we have to remember is to use the proper materials, not only with the right particle from table O, but on the other side with table N, we have our selected radioisotopes. And that third column over is going to tell you exactly what the decay rate is. So if we can zoom in on those a little bit, you'll see lots of betas. You'll see there's a couple alphas, more betas, and I believe there's some positrons on there as well. Let me see, there is, if I remember correctly, there's at least 1, 2, there are 3, 4 positrons. There's a handful of betas and a handful of alphas. So for example, if you were to have to balance out an equation, carbon-14, for an example, is a common one. You talk about that with radioactive carbon dating. So if you had carbon-14, you might only be given the mass number of the isotope and not given the charge. The charge is always what goes down on the bottom, and it's actually the nuclear charge. So what we're really dealing with here is the atomic number, because it's the charge of the nucleus. The charge of carbon would be 6, because the atomic number of carbon is 6, because it has 6 protons. So carbon-14, according to our chart, if we look up carbon-14, it is the second one down, it goes through beta decay. So what that means is that over time, a beta particle will be shot out. And we don't really know when and where, but according to this, the half-life, make sure you check out the other video that relates to half-life, because I'm gonna go through some half-life scenarios. It takes 5,715 years, almost 6,000 years, for half of the amount of carbon-14 to decay. So carbon-14 is not always shooting out particles, but over time it is. And when it does, it shoots out a beta particle. So 0/-1, and then you could use either the B or you could use the letter E. Either or, the lowercase e would work according to table O. Now, what we have to remember is that anything that I start with, I really must finish with, because I'm just losing a particle, part of it's breaking off. So let's say, for example, you had a cookie and you weighed the cookie and you took out one chocolate chip, and then you weighed the rest of the cookie and the chocolate chip. The rest of the cookie and the chocolate chip should add up to what you originally had in your starting mass of your cookie. Well, the same thing holds true here when we do our nuclear decay equations and balanced equations. The masses at the top should add up, and the charges at the bottom should add up as well. We always have to conserve mass and we have to conserve charge. So I didn't lose any mass because the beta particle or the electron basically weighs nothing. So my new mass is still 14, okay? The mass did not change. What does change though is my charge. And what we have to remember, this arrow basically represents an equal sign. So 6 is equal to -1 plus something. Or we could say -1 plus something is equal to 6. Or if we're looking at it backwards, or depending on if you wrote it the other way around, some number -1 equals 6. So therefore, that would be a 7. So when we do our math checks out. Everything on the top adds up to 14, and anything on the bottom, both sides, adds up to 6. But now we have a different atomic charge. If the atomic charge, again, is based on the number of protons, we would then go and we would refer, if you don't have it memorized, we don't necessarily expect you to memorize it, but then we would expect you to be able to go find it on the reference table. So you're gonna look up on the periodic table atomic number 7 and see that atomic number 7 is nitrogen. So when carbon decays, it turns into nitrogen and releases a beta particle, okay? So with beta, our final product always has an atomic number higher than the element that it started with, okay? It's always going up. Now how that happens is actually a neutron turns into a proton, okay? It may seem kind of confusing, but a neutron turns into a proton. So again, let's say I have a neutron here. We know a neutron is neutral. That neutron could actually be made of a positive side and a negative side, or at least a positive part and a negative part. So if I have a negative part, a really tiny negative piece fly out of that, but the mass hasn't changed, so I've lost a negative part, there goes my electron. When I lost my negative, what I'm left with now is the positive. So a neutron has become positively charged, and we know the positively charged particle inside an atom or a subatomic particle is the proton. So when we look up protons, the atomic number is based on the number of protons. So the atomic number goes up, we have a new element, okay? That's why this is called transmutation or natural transmutation, because it naturally happens over time. We cannot change it, we cannot influence it, we cannot heat it up or, put some acid on it or break it up into smaller particles. We don't know when they're gonna happen, it's just naturally gonna happen over time. But this naturally happens. We start out with one material, we end up with different products, but we're starting with just one material. We're not doing anything to it, okay? So with beta decay, we are going to go up. With alpha decay, we're gonna see something different happen. So we'll put another example out here. We'll turn back to table N, and you might see something in the Regents exam that shows or says which one represents alpha decay, or maybe you have to actually do the balanced equation for alpha decay. So I'm gonna pull out the first one I see here, francium 220, so 220 FR. And again, the reference table only gives you the mass number. That's the isotope of the mass, and it gives you the actual element you're using. So obviously, if you're gonna have to have it memorized or not, I would not recommend memorizing the periodic table. I'd recommend knowing and understanding how to use it. So down in the bottom left corner is FR or francium, which is atomic number 87. Now that goes through alpha decay. So whether you use 4/2 He, or you could use 4/2 with the alpha symbol, you could use either or, both would be acceptable. I'm still going to do the same thing that I did on the previous example. I have to add up my masses both on the left side and the right side of the arrow, and they have to match up. So if I started with 220, that's 4 plus something. Or I could say 220 and I lost 4 because that helium particle was shot out. So I lost 4. That means I'm left with 216 because 4 plus 216 adds up to 220. 87, if I lost 2 positively charged particles, that means I lost 2 protons. I'm now down to element 85. So 2 plus 85 equals 87. So again, consider your arrow as though it is an equal sign. Anything we start with, we must finish with both on the top and the bottom, independent of one another. So I'm gonna look at the top numbers first. 220 is equal to 4 times 216. And then separately, I'm gonna do 87 is equal to 2 plus 85. So again, I don't recommend that you memorize this, but I basically recommend and appreciate when you learn how to use it. So now we gotta find element 85. Element 85 is way over here on the right side, AT. And so now we have our new element, okay? And that is alpha decay. So we have an example of alpha decay, we have an example of beta decay. With beta decay, the atomic number went up. With alpha decay, our atomic number always is gonna go down 2, and the mass is gonna go down by 4 because we lost that helium particle. Now, with the gamma ones, they pretty much remove gamma off of the reference table. They may mention it in the state exam, but the big thing with gamma is that there's no change in the mass, there's no change in the charge. So the element you start with is the same element you end up with. And I believe the state really wants to see some differences when you're going through and doing your math. So hopefully you found that beneficial in how to do alpha and beta decay. Make sure you check out the rest of the videos, subscribe to the channel, and so that you can see when I have other chemistry updates or other things that you may find interesting to you over time. But again, this was for alpha and beta decay, and I'll be having other videos out there with radioactive decay and all sorts of aspects of chemistry. Hope you enjoyed this one. If you have any questions or comments, just leave them in the description below. Thanks.